equations. This isn't too bad, is it? So here's the idea with exact equations. I think I started this last time. We have a differential equation of two variables, and um, uh, back in the multivariable days, you might remember doing this, that we have this thing called a differential, and the differential dz is just the derivative of f with respect to x times dx plus the derivative of y with respect to x times dy. So this was used to approximate different things back in multivariable calculus, but we're going to use that to solve differential equations. Specifically, we're going to pretend that f of xy is equal to constant, and if f of xy is equal to a constant, that is z equals a constant, then this differential ends up being zero, that one there, because constant derivative of a constant is zero. So we're gonna sort of leverage that to solve some differential equations. In particular, let's just take for a moment, take a look at this differential equation, which looks like a nightmare, doesn't it? It looks horrible. You know, how would you solve this thing? You got 2x minus 5y times dx plus this stuff times dy equals 0. So at first glance, you think, oh, that's terrible. You might try to make it separable, like put the dy over dx, but I think you probably can figure out that this is not separable. It's not linear because of this y squared here. Yeah, this is not going to be a happy moment when you try to solve this. But when you notice that this thing happens to be the derivative of a function of two variables, then it becomes super easy. In particular, let me just point out that this is the derivative of this function. Just a minute, I got to write it down here. I have x squared minus 5xy plus y cubed. So let's just take a look at this function. Imagine that this is equal to z, and let's do the differential for this. That is, what is dz? And then we'll link it back up here. So take a minute, figure out your derivatives. And if you're not sure, basically you're just going to be doing derivatives. Do the derivative in the x direction, do the derivative in the y direction. You can do it. All right, Rachel P. Rachel, do you have the derivative in the x direction for that nasty thing? Ooh, nice. That's perfect. And so since we're doing differentials, we're going to write it like that. And then we just need the differential for the other way. So Andrew, what about the derivative in the y direction? Wait a minute. Isn't that? It is exactly that. And so we have joy because we can just basically say that this is the solution to this differential equation. Well, it's not exactly the solution because remember, what I said on the last slide is that we want this thing to be a constant. If this thing is a constant, if z is a constant, let's just put a constant here, then dz, the derivative of a constant, is going to be 0. So that's the way that this is going to shake out. And then now, of course, you say, okay, now we have a differential equation. This is the general solution. And if you want to know what C is, you better have some numbers, like an initial condition to plug in. Okay, so let's see if we can do this for an actual differential equation. Just a minute. I want to pick a good one. Let's see. Let's skip ahead to this one. Yeah, that's a good one. So let's take a look at this one. And I have the solution method on a different slide. I've skipped it because I think it's more fun to, let's see if we can muddle our way through. And then we'll go back and sort of talk about the step-by-step of how to do this. So this is, I'll tell you right now, this is an exact differential equation. So my goal, here's my goal, is I want to find a function of x and y, which equals a constant, where the derivative, so the derivative of the function with respect to x should equal 2xy, which is that one up there. And I want the derivative of the function with respect to y, sorry, those are partial derivatives, whatever, to equal x squared minus 1, which is this right here. So your challenge, should you choose to accept it, is to come up with that function. The function whose derivative in the x direction is 2xy and whose derivative in the y direction is x squared y. I'm confident that you can come up with a function that will do this. I'll just give you a minute to do it. Did the key get fixed? Yes. Sorry. Well, some of you know it in your head, don't you? Because it's so easy. And some of you are completely befuddled, which is fine. We'll get it both. Well, who's got it? I don't want to pick someone out of the blue here. Does anyone have that function? You got it? What do you got, Zachariah? All right, let's double check. Let's see if, so this is the function he claims is the solution to this differential equation. Let's find out. The derivative of that function with respect to x is indeed 2xy. Oh, that's beautiful. And then the derivative of that with respect to, hey, it worked. How did you do that so quickly? That's so good. I feel like we've done this in multi at some point, but yeah, that's exactly right. You take the antiderivative of this one, and that's what, x squared y, antiderivative with respect to x. Do the antiderivative of this one with respect to y, that's going to be x squared y minus y. And so we're going to have both of those things to make this thing work. And sure enough, it works. So that is actually it for this lesson. So we're done? No, we're not done. Let's go through this step by step. And there's a little rule that you can check to see, because not all, here's the thing. I think I've got this actually written, so I don't have to say it if it's just typed out. Just a minute. Not all functions, yeah, here it is. Not every differential equation that looks like this is going to have a function. So we need to know when would we have this situation where this works. So just so that we have notation down, because I just introduced an m and an n. The m and the n, they refer to those two things. So I'm just going to circle these up here so that you know. This one, that one is m. And this function, the one that's multiplied by dy, that is n. So those are those two functions. Oh, by the way, one last thing about this, and then we'll do it a little bit more. Just a sec. Ooh, I'm sorry, I've got so many people wanting my attention. I shouldn't look at my phone when okay. I just want to know if my wife gets her appointment so I can tell you. But there's other people that seem to think that I'm important. Okay, so anyway, that's m on the left. N is the 1 times dy. And so when I say something like this, that not every differential equation that looks like this has a solution, that's what I'm referring to. I'm saying that you don't know for sure, but we can check, and we're going to use a theorem from multivariable calculus that we had used when we were doing, so this is similar to vector fields, and specifically the, the conservative vector fields. So if those are ringing bells, that's fine. If it's not, don't worry. But it's almost exactly the same procedure. So the idea here is that if you have a unified function that will give you both of those, then we could do sort of switch the derivatives and see if things match up. That's the idea. So in other words, this one, the one up here, the m, that's the derivative of f with respect to x. And the n is the derivative of f with respect to y. And so if we just switch it and do the derivatives the other way, things should match up. So here's the rule. So it's not exactly the vector fields. The vector field thing, you had to have the negative. So it's just that they're the same. So if they're exactly the same, when you mix up the derivatives, if you will. So here the m corresponds with, I'm just going to toggle really quick. The m corresponds with the one that's times dx originally. So you could think of this as being, well, I've got to do that derivative with respect to y now. And then the n is the thing that corresponds with dy. And so you could think, oh, I've done dy, I've got to do a dx. So if this is the case, then we say that we have an exact differential equation, and then you can solve it using a really simple technique that actually, whoever it was, Zechariah, he basically said what you do. you do antiderivatives, and you see where they overlap. I like the way he put that. Okay, so let's just double check really quick one thing, and then we'll do the technique, and then we'll do a couple of examples, and then we'll go home or go enjoy this. I need to go for a bike ride this afternoon. It will help me, at least my mental space. So first of all, let's check this and see if this is true with this one. We know that this is going to be true, but let's double check. So is this exact? Exact. That's the first thing normally you would do. We already know the solution to this, but we're going to pretend we don't. So we ask, is this exact? So I need to do the derivative with respect to y. And this thing, I'll do the derivative with respect to x. So let's just go down and see what happens. So let's pick a couple of randos. I know you can all do this probably. So Rachel J., you know how to do the derivative with respect to y of that first one, don't you? 2x, excellent. And then we got one more. I know it's so easy that it's kind of embarrassing. Okay, Zechariah, what about the derivative with respect to x of the one to the right? It's also 2x. Look, they are equal, and so we are happy. And so anytime they're equal, that means these are exact, and you can go through the procedure. Let's take a look at another one just to see how this works, and then I'll go through the procedure. So here's the second one. I know that one looks much more crazy and annoying, but don't fret. Here's what we're going to do. We're going to pretend that this is like separable. You know, use the separable technique to sort of separate, although it's not. But here's what I mean by that. Do a cross multiplication. So you have y times 1 minus x squared times dy is equal to xy squared minus cosine times sine times dx. Okay, so you see what I did there? I just sort of did the cross multiply thing. And now we're not quite ready. We can't yet apply the rule. You got to move everything to the left side. So that's the final, and then we can use this rule. So negative, oh, you know what I could do? Just a minute. Let's, instead of negative, let's do it this way. Hopefully this won't throw you too much. Cosine of x, sine of y, sine of x minus xy squared dx plus y times 1 minus x squared dy. Writing to, my mind is going quicker than my pen, I think. That's my problem. Okay, now we've got it in order. Now we can check to see if this is exact. And the way you see if it's exact is you take this part and you check what is the derivative with respect to y, and then take this stuff and do the derivative of this with respect to x. So take a minute and do those two things. And I'll just write them down here. I'll find 2 volunteers. Well, Asal, what do you think of that first one? The derivative of cosine x sine x minus xy squared with respect to y. Yeah, that one. So yeah, and all of those are x's. So the nice thing about the x's is that they don't have a y. So you can ignore them basically. Treat them like a constant. So just worry about that one. Yeah, well, leave the x there, but minus x times 2y, very good. So minus, maybe I'll write it as 2xy. But so hopefully everyone sees that, like, if you remember in multivariable calculus, if you're doing the derivative with respect to x, you treat the derivative with respect to y, treat the x's as if they're constants. We don't care about them. They're nothing to us. So we don't care about those. The x, treat it like the number 4. You know, if it was the number 4, you would multiply by 2 and be done with it. All right, next one. Adric, we got the A's first of all here, I guess. Adric, what about the derivative of that second thing with respect to x? So remember that the y, you're going to treat the y as if it's a constant. Let me go over here with this one. So you have y minus yx squared. So derivative of y, derivative of a constant. Yeah, it's just 2, well, the y is going to stick around, but yeah, negative 2yx. Like if that was the number 3, if this was 3 minus 3x squared, you'd do Derivative of 3 is 0. The derivative of negative 3x squared is negative 3 times 2 times x to the first. And look, they're the same. They're the same. So these are exact. That's so exciting. That means that we can find a solution to this. Ooh. Well, we're going to do it. Don't worry. So let's go back and go over the list of rules. I'm just copying this equation down so I don't have to. Oh, come on. There we go. That way I can put it into, I don't have enough room left on this slide to finish this. Okay, so here's the steps. How do you solve this? Number one, start with that. So in other words, you want to rewrite your equation so that it looks like this. You have some function times dx, some other function times dy equals 0. There it is. Next, you're going to check to make sure it's exact. So is this true? Yes or no? If it is not true, you can't do this. There are things you can do if this is non-exact, but you can't do this. So check that. Then if it does, if this is true, then here's what you compute. You start by computing this. Oh, wait, I should back up for just a second. Back up. Let me just warn you. What I'm going to show you is the textbook way of doing this. I far prefer the Zechariah way of doing it. So I will reconcile the two in just a minute. I would have done this even if Zechariah didn't exist. I'm glad you do, though. So just to warn you, especially to warn Zechariah, this is going to look a little bit foreign, but you'll see sort of some of the hints of what we're doing. So we're going to compute the antiderivative, and we're going to remember we're going to be adding a constant, but we're doing antiderivative with respect to x, and so the constant is a constant in terms of y. It could be a function of y. So that's what this is. So I don't like this because I find this confusing. I would say, well, you'll see. We'll just be basically doing this. So, but this is a textbook version. Then you do the derivative of whatever you get here, and you're going to have a g prime of y involved, and set that equal to n of xy. And then you can sort out what g is, and you can, it's just, and then you put it all together. Okay, so that's the textbook method. It's very similar to what Zechariah did, but his method is way easier. So let me explain Zechariah's method. So Zechariah's method is you're going to do almost the same thing. I'll put it over here. Maybe I'll make a line. So what you're going to do is you start by doing the integral of m of xy dx. Now, it's kind of hidden in all of this notation, but down at the very bottom, they actually compute the integral of n of xy dy. I know it doesn't look like it, but it's embedded in that stuff down there. So just so you know, we did both of those. So you do this one. Don't even worry about g of y. Don't worry about that. Ignore it. And then do this one, which is embedded in here. Now, the thing that is a little different when you do it his way and my way, honestly, I would have taught you this, like I said, because it's so much easier than all of that, is when you get done, the price you pay is that you have to think a little bit about reconciling these two. In other words, you want to see where do they overlap, where do they not overlap, and make sure all the components are accounted for. So there's a little bit of accounting at the end, but I think it's a lot easier. So let's actually do this. So essentially, we're going to do those two integrals and then see if we can put them together. Okay, so let's go over to Notability because it's easier for me. And there we go. Okay. There. Come on. Okay, so So there's that equation. So let's, I think we already did the rewriting, but I didn't copy that part. So let me just rewrite this. So we have, what was it? Cosine of x, sine of x, minus xy squared times dx. And then we have y times 1 plus x squared times dy. Okay, so yeah, I think that's where we were. So here's the method. It's kind of, it's the same, only it's just sort of getting at the answer a little different way. Is I'm going to take this thing on the left and integrate that with respect to x. Because indeed, this is a derivative with respect to x. And then I will do the same thing on the right, but I'm going to integrate that with respect to y. Oh yeah, what do you know? Yeah, my head isn't where it should be. So I can just dump anything. That's what actually the doctor was hilarious. She said, you know, that yeah, she said this is going to happen next week. And I said, well, how do you know? And she said, because I'm going to say cancer and everyone will stop what they're doing. And like she's like, cancer, that's the you say that word and everyone comes running and like it's kind of so I could do the same here. It's like cancer. Oh, she wasn't here for the cancer. You have to ask your friends. Yeah, there's cancer. Okay, but anyway. So yeah, so if I make mistakes, that'll be my excuse, at least for the next month. Actually, 6 weeks. 6 weeks is the recovery. There we go. Okay, so let's do these. I think probably the one on the right is going to be easier for you, isn't it? Go ahead, do the one on the right. Be happy. I'll help you with the one on the left. Let's get the one on the right out of the way so we can be happy. 245, we're doing great. All right, Claire did the one on the right. You did it so quickly that you didn't even have to write it. What do you got? Oh, sorry, I put a, see, cancer. Sorry, I should not joke, I know. Okay, so 1/2 y squared, which is exactly what you said. Maybe I should, here, why did I do that? Yeah, you distributed is all that, yeah. But your distributing of it is way better than what I just wrote. So I'll 1/2 y squared x squared. Is that better? That look good? Okay. Okay, now let's deal with the right, that's the right-hand side. So there we go. I'll make a little line so we know that there's a line of demarcation there. On the left, let me help you with this. We're going to have to do this separately. So this piece is going to be easy. So we'll pick someone to do that piece. And then if you want to show off, you can do the other one. But Austin, what about this piece right here? What's the antiderivative of xy squared with respect to x? Oh, so 1/2 y minus 1/2 y squared x squared? I know. Yeah, okay, yeah. I was just, I knew that that's what you meant. I knew it. I just was fooling with you. Okay, so that's good. So does anyone want to show off with the cosine x sine of y or sine of x? Who, what? Tyler knows it? Yeah, perfect. So I'm guessing you use substitution or did you just do it in your head? Yeah, this is a substitution. You let u equal sine of x, du is cosine x dx. And so you can kind of see how that's going to shake out. Or you can just trust Tyler, which I think is pretty good. You're going to be on the money if you do that. And just say, oh, it must be correct. So sine of x squared. And then after you trust him, you say, wait a minute, I shouldn't have just trusted him. Let's check. Do the derivative of this, use the chain rule, multiply by 2, and the derivative of sine is, oh yeah, it's correct. So good job. So yeah, but you could have used substitution. That's fine. Okay, now here's the tricky part. And this is the part that apparently Zechariah knows how to do, but let's see if we can all figure it out. And that is, we have to sort of reconcile these two. So what I want to do is, I like the word he used, is figure out where they overlap. Let's see. Oh, look, there's that one part that that Austin was referring to that is the same between the two. So those are going to be the same. So down here, what I usually will try to refer to this as is I call it the union of the two. Like when you're doing the union of two sets, you don't include anything like twice. Like if I did the union of this class with my previous class, Rachel J and Cooper S are in both classes. They're not going to be in that union twice. I mean, I don't know, maybe you have an evil twin that's running around, or yeah. But anyway, so they'll just be once, when the overlap gets counted once. So it's kind of like that. It's like a union. So let's do that. So here's that overlap, 1/2 y squared x squared, stick it in the middle. And then let's deal with the stuff that is not in the overlap. This needs a 1/2 y squared to be happy, and this one needs a 1/2 sine squared x to be happy. Now everyone can be happy because we have stuff over there is all taken care of. The stuff over here is taken care of. And you can also double check if you don't believe it and do the derivative of this whole thing with respect to x. You'll get this because this is no x's, so it's constant. So derivative of this is 0. And then if you do the derivative with respect to y, you actually get that up there because this here is just x's. It's constant with respect to y. So derivative of that is 0. So this is my answer. Well, it's almost my answer because I have left off the initial condition. But the initial condition is always easy. There's almost no work to be done to get the initial, to deal with the initial condition. This is the hard part. Now that we've got that, let's deal with that initial condition. Notice that this means that x equals 0 when y equals 2. So let's plug it in. X equals 0, y equals 2. So that's 1/2 sine squared of 0 minus 1/2 times 2 squared times 0 squared plus 1/2 times 2 squared. All of that equals c. So here's what I mean by that there's almost no work to be done. You remember how the constant, sometimes you have to do some algebra and a little bit of moving around? Nothing. You just do the calc, you just plug in the numbers and you're done. C equals 2. And then if you have an iPad, you just do this, copy and paste. Copy and paste. And then we've got the 2, and there is, put a box. There's the answer. All right, what sort of concerns, questions, fears, worries do you have? Maybe none, which is fine. So I can, when I put these on, everyone looks blurry, but now you look clear, but then I can't see anything up here. So. Another thing about getting old, you're gonna have to wear glasses. I used to make fun of my parents, and I feel so bad about that now. Come on, Dad, can't you read? So bad. All right, no issues? Okay, let's take a look at anything else that can go wrong. We can't remember if there is anything. Let's see. What is this? What's that? Oh, fascinating. That looks cool. It must be a solution curve to this. So yeah, that must be this. Yeah, so that must be like if you were to draw a bunch of different, like here's the thing. Let's go back here real quick. Here, this thing, that thing, this one here. If you put different numbers in there for C, of course you're going to get different curves. But if you put them all on the same graph, you're going to be able to see all the different solutions for different initial conditions. And here's what you'd see. And the blue one is y of 0 equals 2. It's right there. But you have other solutions that are little loops and other solutions that do weird things. It's kind of cool that there's all these different possible solutions to this differential equation. Okay, but that's that. Let's see, we don't want to deal with this, I don't think. I hope not. Just a minute. Let me check before I dismiss that, because we do have time. We could deal with it. Hold on. Because I know I just took your homework, is the homework that I gave my class the last time I did this. So let's see if we have to deal with this thing. Oh yeah, I guess we do. Okay. I was trying to avoid it, but we were going to do it. Okay, so back here, I scroll back. This statement, not every differential equation of this form corresponds to a solution. So you might say, well, what if you have a differential equation that does not fit the pattern? Well, let's see what such a differential equation might look like. It might look like this. And so let's take a look at this briefly and see what happens if we do, well, we'll see. Let's first of all take a look at this. We have, whoops, it's going to annoy me, isn't it? There, that's a little bit better maybe. So let's check what is the derivative of this with respect to y, and then we'll do this one, the derivative with respect to x. So I need to find both of these derivatives because this is where the initial stages to see if this is exact. This is the first step. So let me find some volunteers. Max could do it, but he's not here. Cooper C knows. Cooper C, what's the derivative of that first thing with respect to x? Or no, y. We're doing.
You can't be angry with that.
No, Cooper C.
Yeah. Oh. I'm too tired for this.
Yeah, me too, man. I'm with you.
Yeah, no,
Claggett. Maybe I'll just call it. You don't want to be called Stiegel, though, I thought.
no, I never said that. He calls me Steve all the time. So she.
Okay. You henceforth will be called Stiegel. Okay, Claggett or Cooper Claggett. Yo, it's just, derivatives, thank you. He's like, I'll just sit back here until they finish arguing. Okay, Joshua, where are you? I can't see anything. Oh, there you are. It's amazing. It's just shocking how bad it is. Okay, so what's the derivative of that with respect to x? What? It's not x? Look at this. Oh, they're not the same, but they're so close. So when this sort of thing happens, sometimes you can fix it. And so we're going to fix it. So the way you fix this, I know but it's not as bad. You remember how we did this with linear equations? You have a linear equation, you can't solve it, but you use this sort of product rule in reverse business. So we're going to do something similar. It sounds scary, but here's the deal: is if now this is only in certain special situations, if it's the case that when you take these two derivatives, take the two derivatives and divide them by one, take the difference of the two derivatives and divide them by either in or m. There's a little bit confusion as to which one, but and if you end up with a function of a single variable when you do this, then you can use an integrating factor that looks sort of similar to your linear equation integrating factors. So that's what these are. So let's talk through this with this one. So the first step, you'll notice that this is those derivatives that we just did. It's just that in one case, you're doing m minus n. In the other case, it's n minus m. So let's go ahead and we'll do this. We'll do m sub y minus n sub x. Let's just do that. That's going to be x minus 4x, which is negative 3x. And of course, the opposite, n minus m, is going to be the opposite, which is positive 3x. So that, just get that out of the way. And now here's the trick, is we're going to take that, and if you put the m first, then you divide by n. And if you put the n first, you divide by m. And if what you end up with is a function of one variable, that's going to be the key to doing this little technique. So let's do this. So in this case, the m is first, so I divide by n. So this one gets to, I don't think that's going to be, I'm not even going to bother. So you would take this, divide it by this. That's not going to be a function of one variable. There's no way. There's too much junk there. I'm not even going to try it. Well, I shouldn't say that because then you'll take that as justification for saying that when you're taking your test, but you should try. But anyway, now let's do it with the other way. So we'll take this one, 3x, and divide it by m, which is this. So 3x over xy. This is a function of one variable. Now, it can't just be a function of any variable. It has to be a function of y. So we did this one down here. So when it's just a function of one variable, in particular when it's a function of y, then you can do this little trick and use that as an integrating factor. So let's try this. Oh no. Oh no. Why did that happen? Here we go. I think I'm going to run out of room. We'll try. Okay, so let's get our integrating factor. That happens to be a function of just y. So my integrating factor is going to be e to the integral of that thing. Hopefully you remember from your linear equations days last week that when you have something like this, you should be excited because you can just do this, e to the natural log, 3 natural log of y, and that's going to be e to the natural log of y cubed, and that's going to be y cubed. Now in this case, we don't need the plus or minus because we just need an integrating factor, and this one will work. So plus or minus doesn't matter in this case. So y cubed, let's use it. Let's see what happens. And I think at this point, do I need to? Yes, I do. I need to switch to Notability. Give me a sec. Here, I'll just highlight everything. And then once we're done with this, we'll be done for the day. It's going to be exciting. Copy and delete. Give me a sec. Put this up here. Beautiful. Paste it in there. Perfect. Okay, so that's our integrating factor. What that means is that I'm going to take this and I'm going to multiply it by everything up here. That's what an integrating factor is, right? You just shove it in there and hope for the best. Okay, so let's do that. We have xy times y cubed times dx is no, not equal to, plus 2x squared y cubed plus 3y to the 5th minus 20y cubed. I think I got everything right there. You can double check my, I did y cubed times that trinomial, and I think I put it in there correctly. Yeah, I think I got them all. Do I have it all? Okay, now, at this point, if you have done your calculus correctly, this is guaranteed to work. But let's not count our chickens before they're hatched. Let's find out if this is indeed correct. Here, maybe I'll just point out that this here is xy to the 4th. Okay, so we need to do the derivative. We'll do it again. Derivative of this with respect to y. See what we get. And then do the other one with respect to x. So let's see. I think I've cycled through everyone, have I? No, surely I haven't. I haven't talked to Luke. Caden, what's the derivative of this first one with respect to y? Did you say 4? I heard a 4. 4xy to the 3rd, you said? Okay, very good. Yeah, derivative with respect to, I thought, yeah, it is hard when you get old and you can't hear as well. And then this one, we're going to do the derivative of this with respect to x. And let's see what we get. So this time we do get Luke. Luke, what do you think of the derivative of that mess with respect to x? Ooh, wait a minute. All the other stuff goes away. Look at that, they're the same. Happiness and joy. So here's the key is if you get something like this, sometimes you can get lucky with an integrating factor, which I know is going to be confusing and difficult to do, but I trust that you're going to be able to do this. And then once this is the case, now we can go through, let's go finish this one. I need to do the integral of this with respect to x. So the first thing with respect to x, I'll just do it to save time if that's okay. And then I do the integral of this one with respect to y, 2x squared y cubed plus 3y fifth minus 20y cubed with respect to y. And that is going to be 1/2 x squared y to the 4th. Ooh, I didn't leave myself room. Just a minute. Just slide this over just a bit. It's better. Okay, so that's the first term, then 3y to the 5th will be 1/2, come on, 1/2 y to the 6th, because you're going to divide by 6. So add 1, divide by 6, so that becomes 3/6, 1/2. And then the last one, minus 20 divided by 4 is 5, y to the 4th. And that's it. Now reconciling. Let's compare. Where does this overlap? This is the overlap. Everything else is not. So we just need one of that first thing. And then we need everything else. It turns out there's nothing else on the top line. So we just add in the rest of the bottom line, set it equal to C, and we're done. Isn't that great? That's exciting. And there's no initial conditions. That makes us even happier. Okay, so your homework, you should be able to do all of this good stuff. If you do have questions, let me know. But I will email you as soon as I know whether or not, or rather, assume I have class unless you get an email. I'll do my best. Probably I will know tomorrow. I hope that they let us know. I'll be angry. I'm actually angry right now that they haven't told us.